Hello, my people. I hope we're doing well today. This is the video for our part of our calculus readiness unit. Will also be the material that shows up on the cumulative quizzes. And so just wanted these videos to be a sort of semi-permanent record that you could go back and consult if you needed to refresh your memory. First thing I'm going to do is go through all of the rules of exponents and actually give you not only the rule but give you an example, a numerical example to show exactly the logic behind it. Okay. Now, the first property or rule of exponents, and sometimes it's called the product rule or multiplication rule. I don't ever really name them. It doesn't really matter to me. Is a to the m times a to the n is equal to a to the m plus n. And as we discussed in class, remember that what exponents do, among other things, right? This is not an exhaustive explanation of what exponents are, but one of the things that they do is they enumerate the number of times the base is multiplied by itself. So it's basically, you can think of it in terms of like a counting mechanism. So a to the m represents the number of times that a is multiplied by itself. N represents the number of times a is multiplied by itself over here. So it should make sense that if you're counting the number of times that a is multiplied by itself here and here, that it would be the sum of those numbers. Okay, and it's easy if we do it numerically, and you can have 2 to the third times 2 to the fourth. Because remember what that means. 2 to the third means 2 times 2 times 2. And 2 to the fourth means 2 times 2 times 2 times 2 times 2 times 2 times 2. So however many, 4 times. And then if I want to count them all up together as a single exponent, it's 3 and 4, which gives us 7, which is of course the sum of 3 and 4. So the addition of the exponents is the multiplication because of what the exponents mean. Okay. Similarly, if I have a fraction like this, or I have a quotient, it is going to be the difference, and that should make sense to us because multiplication and division are secretly the same thing. They just run in opposite directions. So if instead of multiplying by a to the n, which would add to the number of a's I have, you are dividing by n a's, and therefore it would be subtraction. And of course you can do it with the 2's again. Let's say 2 to the 5th over 2 to the 3rd. And if we remember that what 2 to the 5th means, at least for our purposes right now, is 2 times 2 times 2 times 2 times 2, like 5 of them, okay? And that's over 2 to the 3rd. So if you're counting after you cancel, then basically all that's left over is 2 squared, which of course is going to be 5 minus 3. So you get 2 squared. Now remember that this also informs us of why anything to the 0 power is 1. Because if I have 2 to the 5th over 2 to the 3rd, this tells me basically the imbalance of the powers of 2, right? If you get a positive 2 over here, it means that there were 2 more 2's in the numerator than there were in the denominator. But let's say you were given 2 to the 3rd over 2 to the 3rd. Well, that should be 3 minus 3, or 2 to the 0. And that 0 power basically communicates to us that there was no imbalance between the number of 2's as factors in the numerator and the number of 2's in the denominator as factors. So if there's no imbalance, then it's the same number over itself, and that's why it's equal to 1. Okay, so basically we take it from a to the m over a to the n, but then we transform it as a to the m over a to the m, which is a to the m minus m, which is a to the 0. And as we've already stated, that right there is equal to 1. Okay? So basically, anything to the 0 power is equal to 1 because it implies a fraction, a ratio of a quantity over itself. Alrighty. Okay, so that's 3 of them down. Let's go ahead and let's do a to the m to the n. Now, this needs to be remembered that this one is the one that is most often confused with this one because they do look really similar, right? So it is not this one. It is not enumerating a m times and enumerating a n times. It is enumerating a to the m n times. Okay? So just in terms of what exponents mean, that should make sense to us. So if we have a to the m times n, let's do it with 2's again, right? It's just basically it's a really easy numerical way to sort of, show it. So let's go 2 to the 3rd to the 4th. Okay? And let's actually contrast that with 2 to the 3rd times 2 to the 4th. Well, 2 to the 3rd times 2 to the 4th, we did something very similar to that, if not the exact same thing, on the previous page, and that gives us 7 2's. But remember that it's this whole quantity that's raised to the 4th, so I'm going to get 4 of these. And that is indeed 2 to the 12th, because there are 12 of them, where here there are 7 of them. Okay? So basically, you just need to be careful about distinguishing this one from this one right here. Those two are confused with each other a whole lot. Okay? Now, let's go ahead and do negative exponents. Actually, let's go ahead and do the power of a product rule. And basically what that says is, in the ones previous, we've been dealing with where the base was the same, right? And the exponents were different. Here, it's going to be kind of turned around. So you have the bases are different, but the exponent is the same. Okay, and this is basically the multiplication exponent analog, right, of distribution. If you were looking for an analogy between this and something else, this property is to multiplication and exponents what distribution is to addition and multiplication. Okay, so it's an analog there. But if we have something like, and let's use an example that has numbers and variables so that we don't think of simplifying it first, right? Because if a and b are both numbers like 2 and 3, we'll just smush them together and then we'll raise it to an exponent. But if I have something like 2x to the 5th, that becomes 2 times 2 times 2 times 2 times 2 times x times x times x times x times x, because it was 2x, 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 and 2x. But of course, all of these parentheses are just window dressing, right? They're simply performing the associative task. And by the associative and or commutative property, I can basically break down those parentheses and reorder them like this, and you're going to get 2 to the 5th, x to the 5th, which if we go ahead and evaluate, the 2 to the 5th is 32x to the 5th. Okay, so there's that one. And it should be no surprise that if we have it, a over b instead, it's going to be a to the m over b to the m. And so let's say we have 2 over x to the 5th. That's going to be 32 over x to the 5th as we apply it. Okay, and that should make sense. And these two go together because multiplication and division, secretly the same thing, just in opposite directions, right? Okay, two more and then we'll get on to some examples. We need to remember that negative exponents, first we talked about a to the m over a to the n, and that was a to the m minus n, right? And then we talked about a to the m over a to the m, and that was a to the m minus m, and that was a to the 0 or 1. We're going to take this one step further, and let's say we have 1 over a to the n. Well, based upon this right here, that's the same thing as a to the 0 over a to the n, or a to the 0 minus n, based upon this principle up here, or a to the negative n, okay? And so, basically if you want to put that in shorter form, a to the negative n, 1 over a to the n is equal to a to the negative n. And that's it, okay? Then the last one is basically dealing with fractional exponents. Now remember that any operations that are inverses of each other, they're secretly the same operation, they just run in opposite directions, right? Subtraction and addition, they both move you unit-wise up and down the number line, but plus moves you to the right up the number line, and minus moves you down left, down the negative end of the number line. Multiplication and division deal with orders of magnitude. Multiplication makes you orders of magnitude larger, division makes you orders of magnitude smaller. Now exponents and radicals are of course inverses. That's why it's squaring and square rooting, cubing and cube rooting, and stuff like that. So it should come as no surprise to us, and I know you've seen it before, that if I have a, the nth root of a to the n is a to the n over m. Okay, and we can do a numerical example of this. Let's say we have the 6th root of 4 cubed. Okay. Well, 4 cubed is, 4 is obviously 2 times 2, but it's 64, so it'd be the 6th root of 64, or 2. But that's also because it's 4 to the 3/6, or 4 to the 1/2, or the square root of 4, which is 2. Okay, so basically when you're dealing with fractional exponents, the power that it's being raised to is the numerator, the radical that's being applied to it, the root, okay, is the denominator up here. And we've seen that before, and we've done examples of that, but we'll do more examples right here. And just to make it really nice and tidy, I'm going to be pulling those examples that I'm doing off of this worksheet. You were assigned the odds. I'm going to go ahead and do some of the evens, and that will get us to where we need to be. Alrighty. Just by way of summing it up, and these, you can call them this. I don't usually have a name for them. I usually just write them up on the board. You can label them however you want. You can name them Bob, Chuck, Harry, Susie, Diane, or whatever. I really don't care. I guess having a name for them is really easy, but basically what you need to be focusing on is, instead of the names, the principles that they actually embody. So, I tell you what, let's go ahead and call it quits on this first video, and in the second video I'll go ahead and do just a couple of examples, and then in the video following that we'll move on to properties of logarithms. As always, if you have any questions, please do shoot me an email. Bye.